In the previous video, we were able to get to this point in the sequence provided here, xn equals 3xn minus 1 plus 1. We are now ready to sort of generalize this. We see that for any xn, we should have 3 to the n times x naught. That should be our very first term, because we see that whatever that term number is, that's the same as the power that we have here in the exponent. And then we have a descending order of 3's. We would, so in this case, have plus 3 to the n minus 1. So that's, if this were 3 to the 4th, this would be 3 to the 3rd, plus 3 to the n minus 2, plus dot, 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 all the way down to 3 to the 1st plus 1. And we should always get that extra plus 1 there because we're always adding a plus 1 outside of the parentheses here. So the first thing that I see is that this is still written in a very non-compact form. So if I wanted to calculate x 100, I would have to compute basically the sum of 101 terms, really, because I'd have to add the plus 1 there as well. But what I see here is that in these terms shown, whoopsie, wrong button. In these terms right here, what I see is that I have a geometric series that looks a lot like what we have up here, that I have 1 plus a base plus the base squared plus the base cubed, etc., all the way up until some power number here. And the way I could condense that whole thing down is by this formula that says the sum of all of these terms with base x will be x to the largest power plus 1 minus 1 over the base minus 1. Now in this case, I see that I have 1 plus 3 to the 1st all the way up to 3 to the n minus 1. So according to that formula, this should equal, right here, this whole box should come out to be a fraction, which will be the base to the largest power plus 1. So this will be n minus 1 is my largest power plus 1. And then the rest of that geometric series formula states that now I'm going to subtract 1 and divide it by 3 minus 1. So this will be minus 1 over 3 minus 1, which comes out to n minus 1 plus 1 is just 3 to the nth minus 1 over 3 minus 1, which is 2. So again, one of the tricky parts of using this is that it's really tempting to want to write 3 to the n plus 1 up here, but again, that formula says that whatever your largest power is here in the series, the numerator component will be to the same power as this plus 1. So because our largest power was n minus 1, this power here will be n minus 1 plus 1. And now what I'm ready to do is I'm ready to compact this down into a simple formula. So x sub n equals 3 to the nth times x naught plus, now I've replaced everything here in the box with what its condensed form is, 3 to the n minus 1 over 2. So what this formula now allows me to do is what we were talking about earlier, which is that I don't want to have to go term by term. I would rather just be able to say, I want the 10th term, or n equals 10, and I just want to do it in one quick step. So just to check that our formula works, let's go back and look at, so this is x, our x0 is 1, x1 is 4, x2, x3. So let's say I wanted to see if my formula will correctly output 121. So that should be x4. So let's just check that x4 is 21. So check. Is x4 equal to 121? So I know that x naught is going to equal 1 because that's my initial value in the sequence. So to get x4, I should be able to take 3 to the 4th multiplied by my initial value, which is just 1. So I'm not even going to write that there. I'm just going to leave it as 3 to the 4th and multiplied by 1 plus the fraction 3 to the 4th minus 1 over 2. So let's see, 3 to the 4th is 27, it's going to be 81, plus 3 to the 4th is 81 minus 1 is 80, 80 divided by 2 is 40, and 81 plus 40 is 121. So notice how we were able to get the 4th term in the sequence without having to iterate through x0, x1, x2, x3, x4. Instead, you could just give me any term number that you want, and I can use this formula to calculate that term for me. So what we have done is this is what's called the solution to the recurrence relation xn equals 3xn minus 1 plus 1. So that's our final answer. Now let's do it again. Let's do it for the Thomson's loan balance problem. And now suppose we want to actually know, the last question is, what is their balance after 10 years? Which, by the way, remember that n is in months. So this is n equals 120 months. So our formula is b sub n equals 0.01 of the, or 1.01 of the previous balance, and then subtract away our payment, which if I recall correctly was 1,800, but let me just double check here, minus 1,800. And we're going to do the same process of the method of iteration. So the method of iteration says start by listing a few terms and looking for the pattern. So the balance after 1 month is 1.01 times the initial balance minus the 1,800. Now to get b sub 2, that's going to be 1.01. So I see that b sub 1 can be replaced with something in terms of b naught, right? This is equal to b1 right here, so I'm going to make that substitution down in the next line. So this is 1.01, replace b1 with what it is equal to, which is 1.01 b naught minus 1,800. And then all of that minus 1,800. This is actually looking quite a bit like our example problem 4, but our base, notice, is 1.01, and instead of having plus 1 here, we have minus 1,800. So we'll distribute this through. Again, don't actually write out what the product of those two numbers is, just leave it as that squared. That's the trick here, so that you can see where this number ends up going. And then minus 1.01 times 1,800 minus 1,800. So now I'll do the same thing for B3. B3 equals 1.01 B2 minus 1,800. And we're going to stop once we believe we see what the pattern is. So let's I at least recommend doing the first 3 terms just so you're really confident in seeing those. So I'm going to replace B2 with what it is equal to in terms of B naught, which is 1.01 squared times B naught minus 1,800. And then all of that minus 1,800, that comes from this second piece here. Okay, so now we need to do that distribution again, and we will have 1.01 cubed times B naught minus, I always seem to forget terms here. Let's back up a second. This should actually be 1.01 minus 1.01 times 1,800. So I just didn't do a good job copying down. So I'm really just taking this expression here, and I'm now copying that down here. So minus 1.01 times 1,800 minus 1,800. All of that, that's just what I've replaced B2 with, and then I have this minus 1,800 on the outside. So that means if I distribute the 1.01 here, I will get minus 1.01 squared times 1,800 minus 1.01 times 1,800 minus 1,800. So I think we're prepared to generalize our results. It looks like if I were to say what is B sub 4, that would the 1.01 would be to the fourth power times b naught, and then 1.01 cubed times 1800 minus 1.01 squared times 1800 minus 1.01 times 1800, and then finally minus 1800. And in general, we could say that b sub n will be 1.01 to the nth times the initial value minus 1.01 to the n minus 1 times 1800. And then I'll have a bunch of these until I get down to 1.01 times 1800, and then finally minus 1800. So I see here that this is very similar to our term in the first example that we worked with, method of iteration. What I'm going to do here is I see again a geometric series. I see 1.01s with powers, but it's not multiplied by 1. They're multiplied by 1800. So I'm going to take one extra step here before we use the geometric series formula to compress this. I'm going to factor out an 1800. That way what I have left is 1.01, and sorry, these are all minuses here. These should all be minuses. 1.01 to the n minus 1 plus ... 1.01 to the n minus 2, all the way till we get to 1.01 to the first. And then if I factor out a negative 1800 here, I'll just have a plus 1. So this right here that I'm about to box up, this again is our geometric series. And what I'm going to do with this now is I am going to condense this using the geometric series formula. So I'll have 1.01 to the nth times b naught minus 1800. And so the geometric series formula says that this will be the base to the highest power in that series plus 1 minus 1 over 1.01 minus 1. Okay, so all I'm using is the geometric series formula given to us in this video. So this will be 1.01 to the nth times b naught minus 1800, and I'll just condense this down a little bit. So 1.01 to the n minus 1 plus 1 is just 1.01 to the nth minus 1 over 0.01. And that's it. So now I can use, just like in the previous example, I could figure out the balance after any given month that I am interested in determining the balance at. And to do that, we first need to plug in our initial value. So let's think about this. Our b naught from the problem is we have a $200,000 mortgage that the Thompsons are looking at. And that $200,000 mortgage is going to have a $25,000 down payment. So because we're paying the down payment up front, that means they're only going to owe the bank $175,000. So coming into that loan, B sub 0 is going to be $175,000. So it's $200,000 borrowed, or the $200,000 value of the house minus the down payment will give me $175,000 left to pay. So to figure out the balance after 120 months, B sub 120, I can plug in all my values here. So 1.01 to the 120th times my initial value, which is 175,000, minus 1800 times 1.01 to the 120th minus 1 over 0.01. And finally, plugging this into a calculator, we get B sub 120 comes out to be $163,498.07 owed after 10 years. You can kind of appreciate what this solution does. So this is our solution right here. This is our solution to the recurrence relation. And you can kind of appreciate how effective this method is because now we don't need to predict 120 months out.